All right, so I said the DOS can tell you about bonding. We care a lot about bonding. Bonding tells us what we can do to a system to change it to how we want. We're ultimate control freaks that want to be able to modulate that, right? To understand those different, the PDOS, the COOP, the HOOP, COHOP, we have to first talk about how do we parse out charges? How do we figure out a bond's really there? To do that, we're going to kind of discuss it through the Mulliken population analysis. And what we're going to talk about is partitioning charge in a molecule. Talk about how do we do that. So charge is an important property. And it really helps us understand bonding. So let's look at an example. So we have 3 molecules up on the board. How would you describe their bonding? So this is a special type of covalency. It is covalent. I'd call it pure covalent. Right, and that's where polar covalent. And then, what about sodium chloride? Yeah, you call that ionic. Why did you split them up that way?
Because that's just...
It's how we were taught. Never trust how you're taught.
Because they have different properties based off of...
Okay, yeah.
covalent character.
What about charge? Say we're going to focus on charge.
Yeah, how much they share, how well they share.
Right, so here, in H2, what's the charge on each H atom? Neutral is 0, because they don't have control over, like, most of the time, on average. When you draw out H2, what we always show these delta things, right?
Partial negative.
Yeah, partial negative, partial positive, but it's not a full charge, right? So we leave it written that way. Nope, I'm dumb. Terrible. I drew it in the physicist way where, you know, I wanted the dipole to point in the wrong direction.
That's correct for dipole definition.
Yeah.
Physics relevant.
Okay. Then what about NaCl? Yeah, what's the charge on sodium? Yep, charge on chlorine. So charge can tell you a ton about the bonding, right? We can use these ideas to look at the DOS and get other information for periodic systems. Okay, am I okay to erase this portion? It's not really super important. There. So now, let's ask the question, how does one partition charge? So like, let's look at the electron density of HF. Did I have you guys already come up once and try and draw where the electron density is of this thing?
Yeah.
Okay.
A long time ago, so we could try it.
Yeah. Everyone's going to have a different point at which they draw, right?
Only you did throw it as.
Right? Because like, where does the hydrogen end and the fluorine begin? It's subjective, right? Really is at this point. So this is difficult to do. You could say, let's use computations to do this. The problem with that is there are different partitioning schemes. Not everybody has the same ideas or even agrees on how should we split the charge up. I write a paper, I do a Hirschfeld charge analysis. The person's pissed off that I didn't do a Bader. I do a Bader analysis, they're pissed off I don't do a Lodvin. They all get mad at one another. They all have their potential uses and their failures too. And some people won't acknowledge their failures. Bader does not like it when you point out that it's not right in many instances.
Yeah, if you put a lithium ion inside a chlorine cage, it's
Yep.
a nightmare.
Uh-oh. Like the computer program or like the actual guy?
Like
No,
actual
we
guy.
used to get our Or we've got tasks. Same with Hirschfeld, but I think it struggles with that situation.
Who is calling me? So, as examples, here's a list of them. Mulliken charges, Voronoi, Hirschfeld, Bader. The list goes on. There's many different types. What we're going to do next time, we're going to discuss the simplest one. Yep. Because it's the easiest to do. People don't like them because it's very basis set dependent. Really only works well for minimal basis sets. Okay. That's all I got.